Hi, everybody. Thanks for joining. My name is Daniel Halpern, and today I'll be talking about resolving the optimal metric distortion conjecture. This is joint work with Vasilis, Gkatzelis, and Nisarg, Shah. So this paper is generally about voting theory. And when you ask the random person on the street what they think about how voting works, it usually looks something like this. So we have a set of voters. This talk will always be labeled by the numbers 1 through 4. And these voters tell us their preferences over candidates. Candidates here will be the letters A, B, and C, by just telling us who their favorite candidate is. And given these preferences, there's sort of one natural thing to do, which is to choose a winning candidate by just counting the number of votes and choosing the candidate that received the most number of votes. And in a sense, this is obviously the right aggregation rule. Of course, there's lots of formal reasons for this and philosophical justifications, but this really is the most natural thing to do in some sense. Things get a little more complicated if instead of just asking for voters' top choice, we ask for ranking over the candidates. Again, it looks something like this. We have the voters, and now they tell us their ranking over the candidates. And again, we're interested in some voting rule that takes these rankings as inputs and chooses some winning candidate. And this kind of ranked choice voting is becoming much more popular all around the world. So especially in the US, states like Maine use it for their primaries. And things like the New York mayoral election recently are all using this different kind of input format. But the issue here is that it's not so obvious what rule we should use anymore. And just to justify this, don't worry about the details of this big chart. This is a screenshot from Wikipedia. But the standard way that people compare different voting rules is through this, what we call axiomatic framework, by looking at which different good properties voting rules satisfy. And we'd hope to pick a voting rule that satisfies many good properties. But a key point of this table is that there's no voting rule that satisfies all the good properties we want. There's no row here that's all green. And that's for good reason. There's several very classic results from voting theory, known as impossibility results, saying that it's actually impossible to have voting rules that satisfy certain combinations of these axioms. And this makes it a little difficult possibly to compare between different voting rules and know which ones we should use in certain scenarios. So this led some researchers to consider a slightly different way of comparing voting rules, a more quantitative approach. The one I'll cover today was first introduced by Gkatzelis et al. In 2015, but this goes back to some more classic work from about 2006 by Prakash and Rosenshine. And the idea is that we don't assume that these preferences are arbitrary. Rather, they're induced by some underlying metric space. So why a metric space? How should we think about this? The metric space is supposed to represent voter and candidate ideologies. So if voters are close to candidates in this metric space, that means they agree with them, let's say, on lots of issues. So they prefer that candidate. So voters prefer candidates closer to them. And the nice thing about this metric space is it gives us a way to assess the quality of different candidates. Right? So this gives us some objective goals. Say, let's pick the candidate that minimizes the total distance from all voters. And we can compare different total distances between candidates. What's going to make this difficult is we're not going to assume that the voting rule has access to this underlying metric space. Voters still will only tell us their rankings of a candidate. This is just ranked by distance now. And the voting rule now is going to try to pick a candidate that works well in the underlying metric space. And so why might it be reasonable to assume that voters and candidates exist in a metric space? I'll give you a few motivating examples from politics that I hope shows you just how general this framework can be. So the most simple example is this one-dimensional metric space you're probably very familiar with, so the left-wing, right-wing spectrum. Again, it might be reasonable to assume that voters and candidates exist somewhere in this metric space, and voters prefer candidates that are closer to them. Now, you might complain that this is too simple, the world doesn't work just like this, so a slight generalization of this is these things, you might see them online, they're called political compasses. So it's a two-dimensional metric space, so maybe this has, one dimension is your views on economic issues, the other is your views on social issues. Again, it might be reasonable to assume that voters and candidates exist somewhere in this metric space, preferring those closer to them. And this is really well studied in political science, sometimes goes by the name of spatial voting. And there's lots of ways you can represent this, maybe like a very high dimensional metric space where each dimension is a different issue, Again, we make no restriction on this, so we just assume they're located in some metric space. So let me be a bit more formal now and give you the framework. So we're going to assume there's a metric over n voters and m candidates. And as metrics do, this metric is going to satisfy the triangle inequality. And the metric's going to induce ranked preferences, right? So the voters giving a ranking over the candidates in the natural way, where voters prefer candidates closer to them. They can break ties however they want. This is not going to change the results. A voting rule, F, takes this ranking profile's input, so just the voter rankings, and outputs a winning candidate. For now, just a single deterministic winning candidate. The social cost of a candidate, we'll say, is the sum of the distances from the candidate to all voters. So our goal is going to be to pick a candidate that has low cost. And how are we going to evaluate different voting rules? We'll use this notion that's called distortion in this literature. So what is this distortion? This is an approximation, essentially. We say F doesn't know what the metric space is. But let's imagine, in the worst case, what is the worst possible metric for whatever candidate this F chose? So, in the numerator here, given a ranking profile, we look at the candidate chosen by F and the social cost of this candidate, and we're comparing it to the best social cost of a candidate we could have chosen had we known the metric space, so the one with minimum social cost. And we look at the worst case over all metrics that are still consistent with this ranking. Of course, if candidate 1 ranks A over B, they have to be closer to A than B in the metric space. So the natural question then is, what is the lowest possible distortion? And just to give you an idea of how this works, I'll actually start with a very simple lower bound that was introduced in the very first paper on this subject. That shows you this really is not trivial. We're not going to be able to perfectly choose the best candidate all the time. So there's a simple lower bound of 3 on the distortion of any voting rule, and it just uses 2 candidates. So how does this work? So we'll have half the voters say they like candidate A more than candidate B, and the other half say they like candidate B more than candidate A. And this is a completely symmetric instance, so what is a voting rule to do? But let's just say choose, without loss of generality, candidate A. So what could go wrong? Well, it's possible that the metric looked something like this. So we have A and B on either side of the line. And half the voters are just about right in the middle between A and B. They're very, let's say, indecisive between A and B. They could almost go either way. They just have an ever so slight preference to A. So these are the voters that correspond to the n over 2 on the left here that said they like A more than B. And the other half of voters are right at the exact same location as B. So they've distance 0 from B and about distance 2 from A, 2 minus epsilon. So these voters correspond to the n over 2 over here that say they like B over A, and they really strongly prefer B to A. And the issue here is that if you calculate the social cost of A is about 3 times the social cost of B. So the voting rule made a mistake. And in a sense, there wasn't really anything the voting rule could do. They had no idea, it had no access to how strong these ranking intensities were, the preferences. So because of that, it had no choice but to make some selection, and it got it wrong, and now because of that, it has distortion at least 3. So a natural question then is can we achieve such a distortion? So now let me just go over some upper bounds. So upper bounds here are distortions achieved by different voting rules. So this is a big chart with lots of maybe your favorite voting rules on here. So things like plurality, where you just pick the candidate that appears first most often, has distortion that's linear in the number of candidates. What's pretty amazing is that even in this very first paper in 2015, Copeland's rule, which is a classic well-known voting rule, actually was known to achieve constant distortion. And you can think about this, this is pretty amazing. So what this says is that it doesn't matter what the metric space is. It could be whatever crazy metric space you want over the voters and candidates. If you look at the rankings induced by this metric space, and then you run Copeland's rule on it, so given access to only these rankings, Copeland's rule will always choose a candidate that has social cost no more than 5 times the optimal social cost of any candidate. And this is regardless of the number of voters, regardless of the number of candidates, and any complicated metric you want. And for a long time, this was actually the best voting rule we knew. So there was a gap between this upper bound of 5 and the lower bound of 3. And that was until 2 papers in 2019 and 2020 that each introduced 2 brand new voting rules that both broke this barrier, achieving distortion of about 4.2. So closer to 3, but still not tightening this gap. And as I've been alluding to, the main result of this paper is that we give a brand new voting rule called plurality matching that exactly achieves distortion 3. So this achieves the best possible distortion over all possible voting rules. It matches the lower bound. So to be able to introduce this brand new voting rule, I'm going to need some new notions. So I have to introduce this graph. So this is called the domination graph of a specific candidate A. And this is a bipartite graph where we have the sets of voters on both the left and the right. And we'll have an edge from a voter I to a voter J exactly when an I's vote, candidate A weakly defeats the top choice of J. So this is a pretty wordy definition. Let me just give you an example of how this works. So let's say the rankings look like this, and we highlight A on the left here, and the top choice of the voters on the right. So these are the same rankings. Let's consider the edges incident to this voter 2 on the right. So what do? We look at the top choice of voter 2. This is candidate C, and we look where does C appear in all the rankings on the left. And then we compare this to where candidate A appears. And whenever A is above C, we'll draw an edge from that voter on the left to 2 on the right. And whenever C is above A, we won't. So the edges look like this. And of course, we can do this for all the voters, and we're left with this graph. Let me just give you a little bit of intuition about why we might care about this graph. It seems a little arbitrary at this point. So first of all, more edges in this graph seem like a good thing for candidate A. For example, if this is a complete graph, that means that candidate A is ranked in first place for every single voter. So this seems like a very promising candidate. Additionally, we can imagine using this graph as some sort of justification for choosing candidate A. So let's say we did want to choose candidate A, and this voter 4 comes and complains. They said, I don't like candidate A. I much prefer my top choice candidate, candidate B. Why couldn't we have chosen them instead? And we can tell voter 4, we can look at this graph, and we can see there's an edge from 4 on the right to 3 on the left. And we can tell them, well, voter 4, had we chosen your top choice of B, we would have made this other voter, voter 3, less happy because they like candidate A better. Now, this is not the best justification for a few reasons. I mean, first of all, why does voter 4 care about what voter 3 thinks at all? But beyond this, this voter 3 is very powerful, right? Because they rank candidate A first. So it doesn't matter who comes and complains. When voter 2 comes and says the same thing, they want candidate C, we can always hold up this voter 3 and say, look, well, had we picked your top choice voter, this voter 3 would have been less happy. So let's make this a little harder for ourselves. Say if we've already used voter 3 to justify to voter 4, we can't reuse them. We'll have to find someone else. And really what I'm asking for, if you think about it in graph theoretic terms, is for a perfect matching in this graph. So I hope that little story maybe gives you a little intuition about why this might be useful. And we actually use this as a very key result. So our 2 main results in this paper is that there always exists a candidate whose domination graph admits a perfect matching. And we can actually use this to show that any voting rule that always outputs such a candidate has distortion 3. So if you always pick a candidate with a perfect matching in their domination graph, they have this optimal distortion. So this ranking matching lemma is actually very surprisingly technical. It doesn't use any crazy techniques, but the proof is very, very long and pretty intricate. So I won't be going over that at all. But what we think is pretty amazing is how powerful this lemma actually is. It's going to let us prove this optimal distortion theorem in a really simple way. And we're actually very excited about it. We think it might have some other implications and other big questions in voting theory, which I won't have time to get into today, but we think it's a pretty cool result. But let me, for now, actually just show you how easy this second proof is, just using the power of the ranking matching lemma. So the proof goes like this. So let's just fix our voters V, our metric D, and then this chosen candidate A that has a perfect matching. All right, so that's just some notation. And what do we want to show? Well, what does it mean for the candidate to have distortion 3? It means that if you pick any other candidate B, the social cost of A is no more than 3 times the social cost of B. So this is what we want to show. And just remember, what does it mean for A to have this perfect matching? It means that if you look at any voter I, they have to prefer A, or at least weakly prefer, to the top choice of the voter they're matched with. That's what it means for this perfect matching. Okay, so this proof is just going to be one big equation block. So what do? We start with the social cost of A. Let's just expand this definition. So the sum of all distances from voters I to A. Now, by the definition of the matching, this is a most the distance from I to the top choice of the candidate matched to I. This is because if voter I prefers A to this top choice, that means they're closer. That's just the definition of preferring under this metric. Right, so it's just the definition of M. This next step is just by the triangle inequality. So you can always break up distances into the distance from the first thing to B, and then the distance from B to the second thing. This next step is actually because M is a perfect matching. So why can we do this? So this first part didn't change, the distance from I to B. But the second part, notice that we're summing from candidate B to the top choice of all voters matched to some voter I. But since M is a perfect matching, it's actually a bijection between voters, right? Every voter is matched to exactly one other voter, and all voters are matched to. So this is the equivalent of just summing over the distance from B to the top choice of the specific candidate I. Okay, so again, we use the triangle inequality, breaking up the second distance to the distance to I. And this final step is because the distance from I to their top choice has to be most the distance from I to any other candidate. That's just the definition of being a top choice. And if we rewrite this and combine these due to symmetry, we see this is exactly 3 times the social cost of B. So that's it. That's the entire proof. Okay, so this is a pretty cool result. We've matched the lower bound. What if we want to beat the lower bound? So this is actually also a pretty well-studied problem. So 2 methods I'll talk about, the restrictions to the metric and randomization, are interesting directions to keep improving upon this. So what's the idea for restricting the metric? Well, remember, this was our bad example. And maybe one way to get around the metric, around this lower bound, is to say this metric is not an allowable metric. You know, why? Maybe there's something weird about this metric that we don't want to include it in our set of possible metrics. But the thing about this metric is actually it's such a simple metric, just being on this line like this, that obvious ways of restricting the metric just won't work. Like, we can embed this metric space into any, even one-dimensional Euclidean space, like very low dimensional, or a tree metric. It's all possible to do. So any of these standard ways of restricting the metric just simply won't work. But if we think about it at an intuitive level, the reason this lower bound is so bad is because half the voters are almost completely indifferent between the two candidates. They're like right in the middle between A and B. So we might ask the question, what if the voters are more polarized? And this was studied in a follow-up paper by Ancelovich and Puzzle in 2016. They defined this notion of alpha decisiveness. They said a metric was alpha decisive if whenever a candidate A is the top choice of voter I, then a distance from I to A is at most alpha times the distance from I to any other candidate. So this means I strongly prefers their top choice to any other candidate. Voters are a little more polarized. So alpha is just some parameter in 0, 1. So, for example, if you choose alpha equals 1, this doesn't convey any additional information. We always knew that voters were closer to their top choice than to any other candidate. But, for example, if you choose alpha equals 0, this means that each voter is exactly located at their top choice, right? They really strongly prefer their top choice to any other voter. They're distance 0. And this actually corresponds to some interesting special cases, say things like peer selection, where n voters are voting amongst themselves to pick a single leader. It makes sense that a voter will coincide with themselves in the metric space. They prefer themselves much more than any other candidate. But different values of alpha give us a guarantee that voters prefer their top choice candidate more than others. And the cool thing about our plurality matching rule is that it seamlessly extends this alpha decisive case. So if we're guaranteed a specific value of alpha, then our plurality matching rule actually achieves distortion 2 plus alpha, so better than 3 if alpha is less than 1. And this is nearly optimal. So we provide a lower bound that's at least, depending on the number of candidates, as the number of candidates gets large, approaches this 2 plus alpha. And what's cool is that a lot of other rules don't extend this easily. Even if they get good distortion, they don't necessarily have better distortion when we're given a restricted alpha. Okay, so that was one way of getting around the lower bound. An alternative is randomization. Right, so again, an issue with this setting is that A and B are completely symmetric, and the voting rule had to choose one. Right, so what if the voting rule could have instead flipped a coin and picked each candidate A and B with probability half? That seems like the most natural thing to do. So this instead yields a distortion lower bound of exactly 2. What's interesting is that we don't actually know how to do much better than deterministic using randomized rules. So, for example, in the 2016 paper, Ancelovich and Postel showed that random dictatorship, so this is just picking a voter at random and choosing their favorite candidate, achieves distortion 2 plus alpha. So using randomization, we were able to do as well as plurality matching. And we slightly improve upon these bounds by giving new randomized voting rules that do slightly better for different values of m. But what's interesting is that as the number of candidates grows large, we don't actually have bounds that are better than the deterministic counterparts. So we're not really sure if randomized rules can improve upon the deterministic results that we already have. And the lower bound for randomized is actually strictly lower. So this is a very interesting direction for future work. Right, so just to wrap up, we'll give you some possible directions for follow-up work. For alpha equals 1, and as the number of candidates grows large, the lower bounds and upper bounds for randomized rule are still just 2 and 3. So there's still this gap, just like there had been for deterministic rules for a long time. I think this is a very interesting direction for problems in the future, closing this gap and seeing if randomized rules truly can do better than their deterministic counterparts. Further, there's lots of possible extensions in voting theory. So we only analyzed strict preference orders where voters gave us their whole rankings. So you can imagine extending this to other input formats, so weak preference orders or maybe approval preferences where voters just tell us a set of candidates that they like and other candidates they don't like. Further, you can imagine not just selecting a single candidate, but selecting a committee of say, K candidates. And here, there's lots of options in how to define the actual social cost within the metric, but this is an interesting direction to see how we can do in this distortion framework in these other settings. What I think is really cool is actually applying this distortion framework beyond just voting, because I think it's very interesting to show the value of using different kinds of information. So using how much do we lose by using only ordinal information instead of giving the full underlying cardinal information. And this has been applied to many other interesting problems in theoretical computer science, things like matching, flow, and cut. But I think this kind of framework is really cool and can show us some interesting things about the usefulness of information. So that's all I have for you today. Thank you so much for watching.